Hello, my name is Luke, and welcome to this series on reinforcement learning, where we're going to cover the basics of reinforcement learning and then look into implementing deep reinforcement learning solutions. So this series is a sort of side branch off of a main series that I've created on deep learning in Pytorch, where I cover a bunch of the concepts around deep learning and show you how to implement many of the popular algorithms in Pytorch with Python in Pytorch. So we're up to reinforcement learning in that sort of series, but because reinforcement learning itself has so many new ideas and new concepts, I thought I'd create this sort of side series where we're going to go right back and cover some of the basics of reinforcement learning itself before getting to deep reinforcement learning and how you can implement that in Python with Pytorch. So this series, this reinforcement learning series, is going to come as a number of videos. The first two videos, we're just going to cover the basics of reinforcement learning. So if you haven't learnt or covered deep learning before, you can go to that Pytorch deep learning series and learn about it there. But these first two videos are purely the basics of reinforcement learning. And then the next one or two will be deep reinforcement learning. So if you don't know deep learning yet, don't worry. In these first two videos, we're just going to cover the basics. All of the code and slides for this series can be found in that Pytorch tutorial GitHub repo. There'll be a link in the description, and it is under section 11, RL, notebooks. You have these slides, the PDF for reinforcement learning and deep reinforcement learning, as well as the code examples that I'll reference throughout the videos. Okay, so with that out of the way, let's get into it. So firstly, a bit of background information and a bit of a motivation of what is reinforcement learning and why do we need it. So we use machine learning, if you're familiar, to come up with sort of automated solutions to problems. It's a data-driven automation technique. With machine learning, we need to define some sort of objective, some sort of cost or loss that we want to minimize, or some objective we'd like to achieve. With that objective, we need to know how to update our machine learning system in order to minimize that cost, minimize the loss, or to achieve the objective. The problem that reinforcement learning tries to tackle is, what if we don't know how to update our system in order to minimize the cost? Maybe there's some sort of disconnect between our objective and what we actually need to do to achieve that objective. To give a concrete example, let's consider a pick and place robot arm. So it's the robot arm that's going to pick up an object from one location and place it in another location. For a simple situation, you could use just a camera with computer vision to detect that object in space, and then, using the kinematics of the robot arm, move the robot arm to the location of the object, pick it up, and place it somewhere else. Right? But for more complicated tasks, more complicated situations, it may be difficult to define the exact movement of the robot arm that needs to take place in order to pick it up and move it. There may be distractions, there may be different backgrounds, moving objects. The target could be moving. In those sorts of situations, the problem can be harder to define, and you might want to use machine learning. But in that sort of situation, how do you frame this problem in terms of an objective or a loss or a cost if you don't really know what actions you need to take? We just want to define at a high level some objective, pick up the block, move it over here, without defining the actual movement of the robot arm. So how can we come up with a framework that allows us to define at a high level some objective we want it to reach, and then have our machine learning system achieve that objective? Well, enter reinforcement learning. So to give a high level overview of where we are in terms of AI and machine learning, reinforcement learning is a subset of machine learning, which is itself a subset of artificial intelligence, which is a very, very broad and not well-defined field, I find. So reinforcement learning is a subset of machine learning. And then when we eventually get to it, deep reinforcement learning is a sort of intersection between deep learning concepts and reinforcement learning concepts as well. So let's define the reinforcement learning problem, or the framework that we want to operate with in order to create a system that can achieve our objective. So in reinforcement learning in general, and we'll go into each of these in more detail, we have some agent. This agent is going to take some observation of the environment. With that observation, it'll decide on an action to take. And then once it's taken that action in the environment, there'll be some change in the environment, and then it will receive some reward or feedback from the environment or from some source. And that reward tells it how good or bad. And this is a very high level overview of how we want to frame our task or objective so that we can use reinforcement learning. So let's go into each of those in more detail. So the environment. The environment is the medium with which we want to interact with, or the thing or the system that we want to interact with. Right, that could be the real world, such as our robot picking and placing objects in the real world. It could be a video game, which is a very popular medium to use reinforcement learning with. It could be a simulation of the real world. It could be a website, so interacting with a web browser. It also could be something a bit more concrete, such as like a power plant or a factory, or some manufacturing process that you want to optimize some parameters to achieve some outcome, right? All these sorts of things we could define as our environment in reinforcement learning. This observation, or the state of the world, is some information that we've extracted from the environment that tells us what's going on at the current time step, or potentially previous time steps as well. So those could be camera frames from a camera. It could be frames from a computer game. It could also be numerical information, such as, the number of lives left, your score, how many items you've got. It could be simpler sensor information, temperature, pH level for our factory. It could be light levels, wheel encoders for our motors, distance sensors. It could also be audio or text data. Again, it depends on the environment you're interacting with. So the agent is the thing acting in the environment. It could be a piece of software or a robot, though you could also consider the robot in our pick and place example as a part of the environment, right? So the actions could be sending the voltage or the current to the arms of the robot, to the motors, and then the robot is a part of the environment, and you send these electrical pulses and it moves the arm, and the arm is the environment. So you can kind of think about it in different ways. So again, we've looked at the task or the goal. This is the thing that we want the agent to do in the environment. Could be getting the maximum score in a video game. Could be stacking the blocks with our robot arm. Could be performing your online shopping, or automating some manufacturing process or optimizing some manufacturing process. Now, the reward, as we said, this is what we use to define or tell our agent how good its actions or its state is. So this is the means by which we encourage or discourage certain actions or behaviors in the environment. It is also what is used to define the goal or task. So previously, the task or goal, this is some high-level conceptual thing that we want our agent to do, and how we actually communicate that to our agent is via the reward, right? And it can actually be, as we'll see, difficult in certain situations to make sure that we've created a good reward signal such that an agent trying to maximize that reward will actually complete the task, right? So we don't tell the agent what we want to do, we give it rewards with the hope that if it tries to get as many rewards as possible, it'll end up completing the task. Okay, so now we've got an overview. How do we actually use these observations and rewards to actually determine what actions we need to take? So we're going to define two more concepts: the policy and the value. The policy is the method by which we decide what action to take. So given some observation of the state of the environment, the method by which we choose the action to take is our policy. The value is how good our current situation is, right? It's an assessment of the current state of the world, right? And depends on what our task is. So you can think of it as how close are we to achieving our task, or more specifically, how close are we to getting a reward, or how many rewards have we gotten, right? So how good is our current situation, defined by usually the rewards. Okay, to start off, we're looking into a reinforcement learning example. We're going to create a simple representation of the world, right? The simplest representation of an environment is what we call a grid world. This is simply a 2D grid that our agent can operate or move around in. In our example here, we're going to have a discrete set of states and actions and relatively simple state transitions. So our agent, represented by our little robot here, can be in any one of these states. And it can take one of 4 actions: up, down, left, or right. If it's on the corner like this and tries to go left, then it's just going to loop back around and stay in the same state, same as going down, or same with the other states. If it hits the wall, it's just going to loop back around. But this is our world. Observations are just which one of the states it's in. So state 0, 1, 2, 3, just an index of the states. Our reward is defined by the batteries here, and our reward is given once our agent reaches the reward state. And we'll go into that in more detail in a moment. Okay, so some more definitions. We have what we call trajectories or rollouts, which is what we define as a single interaction of our agent in the environment. So in order to learn what actions to take, our agent basically does little experiments, little tests of the environment by choosing sequences of actions and then seeing how well it did. And that sequence of actions is a trajectory. It's a trajectory of the agent, or the rollout of the policy. The policy is where we define how we choose our actions. So a trajectory or a rollout is a little sequence of actions that we perform in the environment, and then we collect our rewards if we've got any, and use that to assess how well that trajectory performed, and then maybe change our policy or change some aspect of what we're doing in order to improve next time. So we do this iteratively. We perform multiple trajectories, update. So there is going to be some starting state. In our case, we're always going to start in this bottom left-hand corner. It can be consistent or could be randomized per trajectory. Every trajectory might start in a different location, but for our case, we're going to start in the same location. And there's also terminal states. So terminal states signal the end of our trajectory, right? That's usually is a reward state, or it could also be a timeout state. So you can define a maximum number of steps that your agent can take in a single trajectory. You usually want to define some end point. You don't want it to be going forever. In our case, we're going to have a timeout as well. We'll define that, but also our reward state here will also be a terminal state. So if it ever reaches this reward state, the trajectory will end. Okay, so some bit more terminology before we get into some examples. Not really important for what we're doing here, but it's important to note some context that this trajectory can be thought of as a Markov decision process. I'm not going to go into too much detail about Markov decision processes, but I'm just going to point it out here. A Markov decision process is a basic framework for decision making, usually characterized by 4 values: state, actions, rewards, and probabilities. So states are the entire state space, actions are the entire set of possible actions, and the rewards are the rewards that you could possibly get. So all our states are all of the states in our grid world. The set of actions are the 4 actions we can take, and our rewards, the reward of our battery. In our case, the probability that an action will take you from one state to another is going to be 100%. We're not going to assume that there's any variability for now, but we'll get back to this later. Okay, so let's look at our deterministic grid world example. Like I said, we have our agent, and he can move in any one of 4 directions. If he hits the wall, he loops back around. But what we want him to do is get to the reward state in as few steps as possible. Right, so using this framework and all these definitions, how can we get him to choose the optimal set of actions? So one thing he's going to need to know at this point is the state transition matrix, or a state transition table. What this simply defines is what actions will take you into which states, right? So if you're in state 0 and you take action 0, you'll be in state 0, action 1, you'll go to state 2, etc., etc. It's basically just saying that our robot needs to know that if he goes up, he'll go from this state to this state. If he goes right, he'll go from this state to this state, right? So this is our model of our world. This tells our agent what happens if he takes a certain action in the world. So he knows I'm in state 1. If I take action 2, I'll go to state 0. Okay. So with this, he can take random actions around the place. At the moment, we have no way of instructing our agent on what exact actions it should be taking, but at the start, maybe he just takes random actions and he eventually, at some point during the trajectory, stumbles upon the reward state and gets +1 reward. The question is, now what? Now that we've taken this random trajectory and gotten our reward, what do we do with it? Well, you could just take the exact same set of actions again and again. We know it gets us the reward. But as I said before, we want to make sure that our trajectory is optimal, right? A random wandering around, that trajectory probably isn't optimal. But we also don't know what happens in the other states. We've hit this reward state by taking a particular trajectory, but we don't know what happens in all these other states. There could be, theoretically, our agent doesn't know, a reward in a different state. Again, it's important to point out that our agent knows what actions to take to get into a particular state from a given state, but that's pretty much all it knows at this point. It doesn't actually know that the reward is here. The reward could be anywhere. So it's important to point that out. The agent doesn't know where the reward is. It just knows that it's taking a sequence of actions and at some point hit a reward state. So we may have a godlike view of the environment. We may know exactly where the reward is, but we don't want to build that into our agent. Again, if we knew exactly what set of actions our agent should take to get the reward, then why are we doing reinforcement learning, right? We could just program that in. The assumption is that we know what end state we want our agent to be in, but we don't know what sequence of actions it should take that will optimally take it to that end state or that reward state. Right, our reward function could be more complicated as well. So we could have negative rewards and we could have larger positive rewards. If it just took the same trajectory over and over again, it may miss a larger positive reward. But again, it goes back to the fact that what we want our agent to work out is the sequence of actions. And we're assuming that even though these grid balls are pretty simple and we can pretty easily tell what an optimal trajectory might be, we want it to generalize to more complicated situations. Okay. So what do we do? Well, what we can do is we know that this trajectory gets us a reward, but we don't know if it's the optimal path. An assumption we can make is that states around the reward state, or states that have a few number of actions that need to be taken to take us from this state to the reward state, so there's only a few steps between my current state and the reward state, then that state itself probably is better than other states because it's closer to the reward state. So what we can do is we can take that final reward we got and sort of propagate it backwards along my trajectory, with again the assumption being that states that were close to the reward state, not in physical location, but in time, those states have a higher value than, or better states than other states. So we calculate what we call the cumulative discounted rewards, also known as the returns, for a given trajectory or a given rollout. And what we do is we take that reward and we discount it by a constant value gamma. So in our final reward state, it's just going to be equal to the reward. In the previous state, it's going to be gamma times that reward. And then the next state is going to be gamma times the next return, which was gamma times the reward. So it's going to be gamma times the reward. And because gamma is going to be some value usually less than 1, between 0 and 1, that will decay that reward backwards along our trajectory. So this equation here, hopefully you can see what's happening. If our gamma is equal to 1, then there's going to be no decay. And so if our reward was 1, we're just going to put 1 all along that trajectory. If gamma was 0, then there's only going to be 1 reward, 1 return in that final reward state. So here's a graphical view of what that decay does. So we have time steps on the x-axis here and value all the returns on the y-axis here. So you can see our rewards here. We got a reward at this time step. You can see it's been decayed backwards. Got another reward here as well. You can see that gets decayed backwards first. You can see the second peak of our returns is higher than the first because we're adding the reward at this time step plus a little bit of the reward from this time step. And what we're saying here is that these states here that were close to the reward state are better than these ones because it took less actions to get from this state to the reward state than it did from this state to the reward state, right? So they're closer to the reward state, which means they were closer to achieving the objective. As such as well, that means that these states are actually good states to get into. So you might want to get the reward state, you might want to actually get into that final terminal reward state, but what we're saying is that even getting to a state close to the reward state is good. But we'll get back to that later. To see a concrete example of how this propagation backwards works, we can imagine our agent took the trajectory of these black arrows here, and we got our +1 reward, assuming our gamma is 0.9, usually something like that. We can see how the rewards decay all the way back to our starting state, and this trajectory here of values is our returns. So this is our returns for our trajectory here. So they decay backwards in time. Important thing to note is that the particular return we calculate for a given state is dependent on the trajectory. In this example here, we have quite a short trajectory, and so the return we get for the initial state is quite high, 0.53. But for this example here, we took a much longer trajectory. Right, we might be taking random actions, and you can see the returns we get for the starting state are quite a lot lower, about half. So the return we get is dependent on the trajectory we take. So as I said, this return was supposed to tell us how good a particular state is, but if the sort of how good a particular state is depends on what we do later on, then it's not a sort of a fair metric, isn't it? So what you might think we might need to do is average over many trajectories. So we don't just take the returns from one trajectory, we do many rollouts, many trajectories, calculate the returns from each, and then for every state, find the average return. Now this average return is what we call the value. So this value, as we talked about at the start, is our measure of how good our state is. So we get two different returns, 0.53 here, 0.28 here. You can average them together. Now, you can imagine you might need to take many, many, many trajectories to eventually converge to sort of a stable value for your value. And this is true. So final point here is also important that the value is dependent on the policy as well. So the policy again is how we're taking, how we're deciding what actions to take. So here we're assuming we're kind of just taking random actions. And if you were to take just random actions, do many, many trajectories, calculate the value, you'll get a certain set of numbers. But if you had a different agent, which always say went up and then to the right, always did that, and that was your policy, that's a valid policy, then you could do that 1,000 times, and the value that you get for each state is going to be very different. So just pointing out that the value that you get for each state is dependent on the policy that you have for the decision-making policy. So here I'm just saying that the value is the average of the returns over many, many trajectories. Okay. So just to highlight that last point here, that the value of a given state is dependent on the policy, you can think of this also as the value of a given state is dependent on how good your agent is. So we're trying to come up with a policy that, this action taking process that gets us the most amount of rewards, right? So a policy that is very good will get much more rewards and therefore have a higher value in particular states than a policy that's not so good and that won't get as many rewards and therefore the value of each state won't be as high. So I've got an example here of an agent playing Pong. So the agent is on the right here and it's playing against a computer and it gets a point, +1 point if it gets the ball past the computer, and it loses a point if the ball passes it, right? And on the right here, you can see a graph over time of the value function. So let's watch. So you can see the value starts very low at the start, very negative. So it's anticipating potentially losing a point. So it goes very low. And then as soon as it hits the ball back, you can see the value shooting right back up. The value shooting right back up because now it's anticipating that it might get a point. And then as soon as the ball goes past its opponent, you can see the value goes back down again. The ball's not there. It can't get any more points. You can see it's very similar to this trajectory here. We've got the reward. We've propagated it backwards. After that reward state, there's no more rewards as far as it knows. And so the value drops right back down. Right, let's watch that again. Value shoots back up as soon as it hits the point, and then it knows it's got it back. And then it drops back down to its sort of anticipation state. So you can see it's not very confident that it's going to get the ball back at the start. And then once it's hit it, it's fairly confident that it's going to get the point. And then it gets the point. So now let's look at the value function for a pro player. Again, our agent is on the right here. What you should note is that the value function starts off much higher. So it's much more confident at this point that it's going to get the point. You can see even though the ball's coming back, the value function is still going up. And even once it's hit it back, it doesn't really change much. So the value function is anticipating that this agent is going to get the ball back. There's no chance that it's going to miss. And so the value is just keeps going up. And as we get closer and closer to it actually getting it past the computer, the value function peaks and then drops back down, same as before. So you can see that the value function depends on how good the policy actually is, or how good our agent is. Okay. Right, so how do we calculate this value, or how do we store, or how do we use this value? Well, what we do is once we've calculated the value for a particular state, we can simply store it in a lookup table. And then what we do is we check what state we're in, and we look up the value in that state. And then when we want to decide what action to take, what we do is we use that state transition table that we looked at. We check all the actions we can take. We look at what states they get us into. And then we look up in our value lookup table what the value of each of those states are, and simply pick the action that gets us into the state that has the highest value, right? So that's sort of the policy at test time. All we do is we check our state lookup table, state action table, pick the action that gets us into the state that has the highest value. At training time though, for now, we're just going to be taking random actions. We're going to be taking random actions, and we'll look at more complicated methods later on. But for now, let's look at our first coding example. Okay, so first let's just have a look at this state transition CSV that you should have. And this is just a CSV. So for every single state down the rows here, and every action, it tells us what state it gets into. So state 0 gets us into state 0 from state 0. So that's going left from that bottom left-hand corner. So that just, we will remain in the same state. Action 1 will get us into state 1. Action 3 will get us into state 4. And then action 4 will remain in the same state. So just to clarify as well, that is going to be left, right, up, down, up, I believe. So left, we're going to hit the wall. Right, we're going to go right, and then up and down, we stay in the same state. So hopefully that's clear. So let's look at the first method that we've just covered here, average returns. As I said, we're using Python here. The code is available. So the first thing we do is to define our environment, or define the reward function or the reward grid. You can see it's 0 everywhere except that top right-hand corner where it's going to be 1. You can play around with this and define different rewards if you want. This isn't really doing anything at the moment, but I'm just using NumPy to define this grid of rewards and just setting that top right-hand corner to reward 1. We're going to import the state transition table, CSV, as a NumPy array, and we can look at that state transition table. And if we want to know what actions we should take, or what actions get us into what states. We simply index that with the current state, and that tells us what states we can get into for each of the actions. This function here simply calculates the returns. We take the values. We're not using those just yet. We take that trajectory of rewards, which will just be a list, and we take the states that we're in as well, and we propagate those rewards backwards with some fixed gamma and return those returns for the states. So this is actually our returns. So testing agent here, this is just a function that will perform a single trajectory, a single rollout of our agent. Again, it's going to be choosing the action that gets us into the state that has the max value. And we're just using this to assess how good our agent is. Finally, we've got our training loop. So we're going to do 1,000 trajectories. We can see we've defined our returns log. So this is just logging all of the returns that we've calculated for every trajectory. And then to calculate the values, we're just going to average over those. So each time this returns function is going to give us like a grid like this of the returns. It's going to be 0 in the locations that we didn't visit. And then we're just going to add the returns that if we visited the same state twice, we just add them, I think. So every single trajectory, we get a returns grid, and then we average all of those grids together to get our value grid. So it should be pretty quick. And we can look at the returns for one of those trajectories. There we go. That's the first one, got our reward. So kind of hard to see what the exact trajectory was, but we started here. Looks like we went over here and came back and went up and around and eventually got to the reward state, at which point the trajectory was over. You can see we've also got a timeout of 40 steps max. Okay, so now that we've performed that, we can have a look at our value grid. So this is what we get from averaging over all of those returns, 1,000 return grids. And this is what we get. You can see the values here, and we get something that is pretty similar to what you'd expect, I guess. The states that are closest to the reward state have higher values, and states further away in physical space, because in this particular environment, getting closer in physical space means you're closer to the terminal state. That might not be true for every environment though. Right, so once we have this, you can see that we just need to take the next state that has the highest potential value. But you can see that our score, which is that test trajectory we do, is a bit all over the place, right? We get the reward sometimes, and then a lot of the times we don't, and sometimes we get it, and then we don't for a long time. So it's very noisy. We can have a look at the trajectory for the last test. You can see we didn't really do anything. So the yellow is telling us where our agent was, and it always remained at the same point. And you can see the issue here is that that starting state actually has a higher value than the other two states we can get into. So it just always loops back and stays in the same state. Now this is something that can happen with this method. Maybe we can try and collect more trajectories and see if that improves. Not really. So occasionally it happens, but you can see this method has some issues. So let's go back and discuss what those issues are. So simply averaging over the returns, as we saw, it doesn't really work that well for some reason. The main issue is that traditionally in reinforcement learning, and in our case, the reward signal is very sparse. It has this whole long trajectory, and only at one point do we ever get a reward, and then we need to propagate that backwards. What that means is that, because we've also got this timeout, there are some trajectories that we don't get any reward at all, right? We can imagine our agent, he might be moving up and down and random like we saw, and the trajectory might time out when we're right here. Now, looking at that, you can say, well, this state is so close to the reward state, that should have a higher value than maybe these other states. But because we've taken this trajectory and we've taken random actions and we've stopped right here, well, then we're not getting any reward. The returns for this entire trajectory are going to be 0. But there might be other cases where our agent just goes straight here, straight up. and gets the reward in a very few number of steps. What that means is that there can be a really high variance for those calculated returns, and therefore we might get some funny things happening. Like in our case, the starting state had a higher return than the other states, because maybe, that this state is a corner, and so some of the actions just loop back around, and so we're in this state a lot, and then maybe we go straight to the the reward state. Whereas these other states, we can kind of move around randomly for a long time before we get to the reward state, right? We're kind of less likely to hit these states or move around in these states for a long trajectory. So there's a lot of noise that introduces for our calculation of our value, and that can be problems. Also, having to keep track of all the returns for every rollout is wasteful. So we did 1,000 rollouts. We had to track the returns grid for every single rollout and then average them. So you might ask, why can't we just update that lookup table as we go? And the answer is we can. So some sort of exponential moving average, you might think, and that's kind of what we're going to be doing. So the Monte Carlo update is a different way of updating that value function that helps reduce the noise a little bit, but also means we don't have to log the returns every time. So what our Monte Carlo update does is it calculates the difference between the current trajectories returns, so that current returns grid we've just got, and the current value grid. So the value is, again, the average of all trajectories. The returns is just for this particular trajectory. So we initialize that values grid to all zeros, and then what we do is we calculate the difference between the returns for this current step and the average returns, which was the value. So we calculate a difference and we add a little bit of that difference back onto the value in order to update. So that little update step, calling alpha here, that's similar to a learning rate, and just says how much of this difference do we use. So if the returns for one step are massive, it might have less of an impact because we've scaled this alpha to be quite a small value. But it also means, like I said, we don't need to continuously log the returns. All we need to keep track of is the returns for this trajectory and the value function. Okay, so let's look at the code example for that one. Everything is pretty much the same, except we have this Monte Carlo update now for our value function instead of this returns calculation. Right. So we also calculate the returns, sorry, but this doesn't return the returns, it returns the values. So we pass in the values, the rewards, and the states. It'll calculate the returns, similar to before, but we're not logging that. We're going to use that directly after to update our values. So this is all the same, but we have our alpha value now. You can see alpha is quite small, 0.005. So only updating the value function a very small amount each time. A Monte Carlo update, like I said, we pass in the current values grid and the rewards from the current trajectory, as well as the state sequence from the current trajectory, so we know what values to update. So we calculate the returns first, and then we find the difference between the returns and the values of that trajectory. And then we update that, update the values, and return the new values grid. The testing is exactly the same. This process is the same. Take the action that gets us into the state with the highest value. Right, so let's run our training the same. So the training is exactly the same. It's just this update to the value is different. Okay, let's have a look at now. Oh, jumped ahead at our value grid, and you can see it's much smoother and much nicer. We also have our starting state. We don't round so much. We can see more decimal places. Starting state is less than the next states, right? So we've kind of smoothed out some of the noise, and we haven't had to log all those returns. So it's much more of a consistent gradient as we would expect, where our starting state has the lowest value. And you can see the results from running those tests. We've now converged to always getting the reward within the number of steps we've defined. And you can see we've got a valid trajectory now. We've started here and we've just gone up to our terminal state. Okay, so our Monte Carlo has helped us. But what if I said we can do better? As we saw at the start of this, it's still a bit noisy before we converge. So there is still some noise in the update for our Monte Carlo value update. So if the variance of the returns is high, if we have even longer trajectories required and even sparser returns, there's still going to be some variance. It also means that we need to use a small alpha, as we saw, because if the variance is high, we only want to take a tiny little update step and take a large number of trajectories. So convergence will be slow, as we saw. It also only works if the trajectory is of a finite length. Now, I said before that we have some timeout after a while, but one issue with even the returns calculations and our Monte Carlo update is similar to what I mentioned before. If we had a trajectory where we went up and down and around, and then we timed out in either this state here or this state here, well, if our trajectory or our timeout value was one extra step, maybe we'd get into the reward state. If we got into that reward state with that one extra step that we allowed, then the returns calculated would be completely different, right? Very, very different. So again, what the returns are kind of depends on what timeout we allow, which isn't very ideal, right? If we took one extra step, maybe we'd get the rewards and have a completely different returns for our trajectory. So we want something that sort of can handle that situation as well as the variance in general from taking random actions. So we're going to introduce temporal difference learning, which can help with both of those issues. So we help negate the effects of our noisy policy or noisy rollouts. So for temporal difference learning, we don't actually calculate the returns anymore. So we throw that away, and instead we use the reward directly to update the value function. So we take the current value function and the reward, and we use those only to update the value function. Right. So we estimate the returns with the value function, and we'll see that in a second. And there's no need for returns, which means we can have infinite trajectories technically. Because the returns, we have to start at the end state and propagate backwards. There needs to be that terminal state. But if we don't need to calculate the returns, then we can have sort of virtually infinite trajectories, right? If I were to stop here, we can say that maybe the trajectory didn't end. We've only got a partial trajectory. So I know I'm saying infinitely long trajectories, but we can now consider a single rollout or a single trajectory, not as a whole trajectory, but potentially a partial trajectory. And we want to be able to update our model with a partial trajectory as well. So we can conceptually think of it as being infinitely long, but we're only taking a small segment of it. And then maybe at the next trajectory, we can start where we left off as well. Okay, so what is our temporal difference update? Let's unpack that. Well, our temporal difference update really is just the Monte Carlo update with a few tweaks. So the returns for the current state, if we calculate them, can be written in this form, right? I know a lot of the calculations and maths here I'm going to skip over. If there is some interest, I can create another video, more of a tutorial where we solve some of these calculations by hand. If there's interest, I can go into that, but for now I'm going to kind of skip through this pretty quickly. So you can try and convince yourself that the returns for the current state simply is equal to the reward in the current state plus that gamma times the returns in the next state of my trajectory, because we're propagating it backwards. The returns in this state is just the rewards in this state plus the accumulation of all the next states, or next rewards, but the accumulation of all the next rewards is just the returns in the next state. Anyway, you can try and convince yourself of that. So we can formulate it in this way, but we don't have to use those returns. What if instead of we used the actual returns in the next state, we used an approximation of the returns? Well, what's a good approximation of the returns? Well, it's the average return. What's the average return? Well, the average return is just the value of the next state. So we can approximate the returns of the current state by adding the reward in the current state plus gamma times the value of the next state. All we do for temporal difference is plug in this approximation for the returns into our Monte Carlo update, which is this one here, and we get our temporal difference update. So now instead of using our noisy returns we calculate, we use the averaged, smoothed out value to approximate the returns. And we don't have to calculate the returns anymore. So because we're using the averaged approximation of the returns, the values instead of the actual returns, it means that we do converge a bit slower because we're going to initialize our value grid as all zeros. So at the start, the value function is not going to be a very good approximation of the returns. That value grid is not going to be a good approximation, but over time it should slowly become a better and better approximation, and then we should hopefully converge to the true value grid. It will conceptually actually converge to the real value function, this method as well. I'm not going to go through proving that, but you'll have to take my word for it. But what we've done here is known as a bias variance trade-off. So we've got too much variance in our calculation, and we can reduce that variance by approximating our value with another value that has less variance but is biased. Right, our value function at the start is going to be initialized to zeros. It's very biased. It's not a good approximation, but through this iterative method, we can still converge to the same value in a smoother way. Right. So let's have a code example of our temporal difference learning. Okay, so very similar to before. Now, however, instead of the Monte Carlo update, we've got our TD temporal difference update. And all we do is we take our values, that value grid, rewards from the current trajectory, the state sequence of our trajectory, as well as this next value. So the next value kind of tells us, for our purposes here, I think I just define the next value as always to be 0. No, I don't. Our next value is always 0. However, at the end of your trajectory, you can define a next value as the actual next value. So you can take potentially one more step. You need that because, as we see in our calculation, you always need the next state to calculate the returns of your current state. So once you hit the terminal state, well, there is no next state. So for my grid world example here, I'm saying that the value of the next state is 0 after the terminal state. However, if you had the case where you sort of finished here or finished here in your trajectory, you could allow your agent to take one more step to get a final value, but then you're not updating the value of that final state, right? Because that would require the next state. You don't have that. So you kind of look ahead a little bit to update the value or the returns of the value of the current state. But don't worry about that too much here. I've just done it for completeness, but I do set it to 0 every time. Right. It's just to make sure when you're at the end, you need that next value state, which you don't have if you're in our situation. Initialize. And you can see that my alpha value is a lot larger than before. Quite a lot larger than before because our updates are a lot less noisy. Right, so let's run this again. Test agent is exactly the same. 1,000 trajectories. Let's see how we go. Oh, there we go. So again, you can see our value function is a nice smooth gradient. And you can see the test runs. We quickly converge to always getting the reward within the timeout period every single time after, not many actual trajectories. So we haven't had to train our model for that long, really, or haven't had to train our agent that long to get to converge. A Monte Carlo converges eventually, but you can see it's a lot noisier, takes a lot longer. So just by reformulating that value update, we can see it's taking us far less time to converge to a stable or good value grid or value function. And you can see our trajectory here as well. Okay, so that's our temporal difference TD learning. But we can do even better. In fact, let me go back. We can do even better than that. But as you can see, we converge pretty quickly. So I'm going to make the environment a little bit harder for our agent so we don't converge quite as quick. So I'm going to set certain states with negative reward, and I'm going to make the final terminal reward a lot larger. So you can see in this grid here, if you can make it out, these darker regions here are negative rewards, and the yellow here is our terminal state again with 10 rewards. So these states here are not terminal states. You can see the only terminal state is the final reward state. So it can technically get as many negative rewards as it wants, but can only get one positive plus 10 reward. And you can see basically what we want it to do is go through here. We don't want it to get into these states, which is why we set the reward as negative. Let's see what happens now. I might need to reset my values. Oh, it's already been done. Let's see what happens now if we train on this reward environment. So we've got our new reward function or reward grid, and you can see, we get very close to 10 for the terminal one, but you can see these states here are negative, so these are no good at all. But you can see this state here actually still has a positive reward. What that means is that we probably, when passing through this state, the next state is probably going to be the reward state, so it probably gets a lot of reward from this final state. But you can see it's quite a lot, well, it is still a bit lower than the other state. So the preferred path is still to go through this path here. And let's have a look at our score log. Oh, there you go. So you can see it took a lot longer for our value function to converge to a good state, converging to 10 here every time, right? We could get less than 10 because we get our negative rewards, but you can see it took a lot longer, so it's a harder environment for our agent, but you can see it does actually get the optimal trajectory, avoiding these states as well. So now that we've created a harder environment, can we improve any more from our algorithms? So let's go back here. Okay. So there may have been one thing that you saw that you thought, that's not very smart, and that is our random action taking. So we took random actions in order to work out and explore our environment. But at the same time, we were calculating this value grid, this value function that tells us what the optimal trajectory of our environment is. So why don't we just use that? Well, the problem, similar to before, is that if we, perform a rollout trajectory, calculate values, and then use that value function straight away, well, we're only going to take the same path, or pretty much the same path every time. We need some randomness to explore the environment. And this trade-off is called the exploration versus exploitation trade-off. So we want to use our knowledge, but we also know that we don't have enough knowledge yet. So we need to do some exploration, but we also need to exploit the knowledge we already have to speed up the learning process. So how can we do that? Well, we can do that by changing our policy during training. So instead of just pure random actions, we're going to use what is called an Epsilon greedy policy. So we're going to use that value lookup table similar to the test time, but only sometimes. We still want to take some random actions. It's called Epsilon greedy because we define a variable called Epsilon between 0 and 1, which is the probability of taking a random action. So the probability of taking a random action will no longer be 100%. Some of the time we will take an optimal action. So formally, this looks like this. We're going to randomly sample from a uniform distribution between 0 and 1, so all values have the same probability. We define some epsilon. It's going to be probably something like 0.3. And then if the randomly sampled value is larger than or equal to epsilon, we're going to take the action that gets us into the next state with the highest value, as we do with test time. If it's less than, we'll take our random action. So let's see how this performs. Now, our TD epsilon greedy. So everything's exactly the same, except during the training process, we don't take random actions only. So if you saw that, we took random actions every time. But now we define epsilon as 0.3. We take a randomly sample a value. If z is greater than epsilon, we take the optimal action, take the action that gets us into the highest next state. Else, we take our random action. So our reward function is the same as before, the hard reward function. And let's see how we perform now. Still 1,000 trajectories. And you can see we've got our new value function, value grid here. And let's look at our test. There we go. So you can see we converge much quicker now. I think in this case here, I'm not setting the next value to 0, which is why it's so large. Let me just run that again. There we go, much more similar. So we're still converging very quickly to the optimal trajectory, the optimal path, compared to before. It took around 600, 700 trajectories before we converged on the right thing to do. It's taking, less than 100 this time. And again, you can see we're taking the optimal path, and you can see the values of the value function are actually a lot larger than the ones here, even though everything else is exactly the same. And that's because we're taking the optimal trajectory 70% of the time. So we're more likely in a given state to actually get the reward. Like I said before, the value function, or the value we converge to, is dependent on the policy, and we've now changed the policy. So the value function, or the value grid in our case, that we converge to is different because the value depends on the policy. So we've got much higher values now because our policy is more likely to get the reward, so we get higher values on average. Okay, so that's all I'm covering in this part 1. In the next part, we're going to look at model-free learning. And as I've hinted here, we're making a big assumption. The big assumption that we've been making is that our policy, or our agent, knows what actions to take to get to the next state. So we're heavily utilizing this state transition table. The state transition table is what I'd call the model of our environment. It says to the agent, hey, you take this action, you'll get into this state, and we're using that to work out what action to take. But in a lot of situations, we might not have a model of the environment, or our model might not be very good, or like I sort of mentioned before, we're assuming that the probability of taking, or the probability of getting into a state from using a given action is 100%. What happens if it's not 100%? So in the next video, we're going to be looking at model-free learning. What happens if we don't have that state transition table, which is much more akin to a real-world learning situation. But for now, that's all, and I'll see you in the next one.